Welcome, everybody. Our speaker today is Mahima Mary Mathews. She's going to tell us about cryptanalysis, quantum cryptanalysis. Mahima, go for it.
Thank you, Barry. I'm Mahima, and my background is in computing, basically. Then I shifted to a little bit of security cryptography, and then there was exploration about like penetration testing and that angle, which led to quantum cryptanalysis, and then building quantum resistant crypto systems. So still learning, of course. The exploration focuses on definitely utilizing computing, quantum computing in uh, breaking plus building persistent systems. So, in order to be able to provide solutions, we need to understand what could be the potential threats, right? So, and that's basically all of my background. If you have any more questions, you can always reach out to me about me. Now, let's start with today's session. And before that, I thank Barry a lot for inviting me for this, and Ron as well. Thank you so much. So, sharing my screen, just confirm that you are able to see. I've prepared my slides in Canva. So is my screen visible?
It is? Yes.
Okay, great. This is visible as well, right? Full screen?
Yes.
Okay, great. So today what we are trying to discuss is basically breaking codes in the quantum era, which a little bit of focus on, slightly more focus on quantum cryptanalysis. Of course, we know that there are classical cryptanalysis techniques as well, but our focus will be slightly more on quantum cryptanalysis techniques. So think of this way, like we had a very strong lock, which was considered to be very strong enough. And that lock was actually protecting our entire internet, like entire digital infrastructure. But suddenly, somebody figured out a key which can be like used to open that lock uh, on the basis of quantum physics. That's what is basically quantum cryptanalysis. The key that we, or the lock that we used to consider as very safe, which is actually safeguarding our entire digital infrastructure. Today, that lock can be opened with utilizing certain quantum phenomenons. And that is what is quantum cryptanalysis utilization, the power of quantum cryptanalysis, and how quantum cryptanalysis is bringing in a biggest revolution in security. The power has gone, don't worry, like my internet will be stable. Um, yeah, you're still able to hear me, right?
Yes, we can.
Okay, I'll be in dark for some time, but it is gonna come back. Yeah. So let's start the session discussing cryptology. Okay. So as we just mentioned, we have these cryptographic algorithms, which is actually safeguarding our digital infrastructure. When it comes to like cryptography, you just simply shouldn't be thinking about these algorithms. You should think about the entire transactions, like what we are using right now, right? This session is also being secured using some cryptographic algorithms. So everything digital today has its security requirement aligned with these cryptographic algorithms, right? If these cryptographic algorithms are like broken, our digital infrastructure is vulnerable, right? It can be broken, it can be scattered, right? So cryptographic algorithms, they are not just mere algorithms, they are the foundation behind the security or stability or like confidentiality, integrity, whatever you can pinpoint related to security in this current day in digital infrastructure. The fundamental behind them is a cryptographic algorithm, like or a set of cryptographic algorithms. So cryptography is basically an art of creating codes, right? It is you create codes that are able to achieve certain goals that you target. Now, if your goal is confidentiality or secrecy, you have certain algorithms for that. If your goal is integrity, you have certain goal for that, right? If your goal is authentication, you build algorithms based on that. So based on your security goals, you define or modify these cryptographic algorithms to achieve that. Now, what is cryptanalysis is actually the art of revealing the contents of these coded messages that were intended for somebody else, right? So, like you, without any knowledge, or like you not being the actual intended recipient, you try to understand what those codes are or what those information is there. That's basically what is cryptanalysis. Now, cryptology is actually the combination of both, which is actually the cryptography and cryptanalysis. So, as we said, like building these schemes are very important. As equally, cryptanalysis study is also important, because only if you study the vulnerability levels of these algorithms, you can safeguard the stuffs, right? Like it shouldn't be like if the minute the attackers are getting you the knowledge, or attackers are doing some execution, malicious execution, that's when you get to know your algorithms were vulnerable. No, that shouldn't be the case. It's equally important for researchers to have cryptanalytic study on these cryptographic schemes. Is it my echo or was it somebody talking?
I think somebody was not muted and talking, but I think we're okay now.
Right. Okay. Now let's have a recollection of classical cryptography. In case you are completely new to this area, just wanted to give you a gist as well. So our classical cryptography, by the term classical cryptography, I mean everything that you can run, or it is the fundamental behind this is classical computing. Okay. So that's what I call or refer to as classical cryptography here. So under classical cryptography, the main algorithms include symmetric encryption, asymmetric encryption, hashing schemes, digital signatures. There are so many. Right now, what you have in front of you is basically encryption. Okay. Now, encryption, we use encryption for achieving secrecy. Secrecy means, suppose I want to send some message to Barry, and critically very sure that it's just Barry who should be reading that message. So my target is secrecy, right? So for achieving secrecy, we use schemes like encryption. So under encryption, we have symmetric as well as asymmetric. Okay. Now here, symmetric, you can, from the diagram, it's very clear. You just have one key in use. So if me and Barry will agree onto a certain key, which we would have distributed between each other using some other technique, like we would have met in person and then exchanged it, or like we would exchange it in text by via through some channel, or maybe he'll send it to me via WhatsApp, or trusted medium. Using some trusted medium, this key would have been already been exchanged. That's when we can make use of symmetric encryption. So symmetric encryption is basically an algorithm where we use a certain key, which is like already or pre-exchanged using a certain trusted medium between the sender and receiver. And then we actually, so that the receiver can decrypt the message using the same key. Okay. So that's what is basically symmetric encryption. Now, asymmetric encryption, in the same case, me and Barry, we don't require anything to be pre-sent, okay? We just need to have something called a public key, okay? So I will create my public key, private key combination, and I will share my public key. I can simply announce it. It's not required that I should secretly tell it to Barry, okay? Now, Barry also creates his own public key, private key combination, and he announces his public key. So the information that is publicly available or exchanged through network is just the public information. You don't have to transmit anything secret over the channel or over any trusted medium. You don't have to send anything. So here there is an advantage that you are just having to send the public information over the channel, and you are able to keep your message intact or secure, right? Whereas in symmetric encryption, the overhead of making sure that the key that you're using is being exchanged through a trusted medium is always there, right? But here there is additional overheads of computation, since asymmetric encryption is based on mathematical problems and all those things, which I'll show you in the coming slides. So there is that kind of additional overheads, but we don't have an overhead based on the secrecy achievement scenario, right? Like you don't have to secretly send something and then achieve it. That requirement is not there. I just wanted to say that if you have any doubts, which is very critical, please stop me at any point of time. Otherwise, whenever a doubt comes into your mind, pops in your mind, please do put it in the chat window, which we can discuss at the end. Okay. Now, simply to give you an example of symmetric algorithm, Caesar cipher is a simplest symmetric algorithm. Okay, so here you can see there is a shift of 3. The key is shift of 3. So, like let's say my message was CAD, C-A-D. Okay, so I want to send CAD to Barry. Okay, now Barry and me would have agreed that our shift will be 3. This happens only when we have agreed on to that 3 previously, right? So instead of CAD, I will be sending F, D, and G. F, D, G will be my message. Now Barry will receive this message, and since he knows that we had agreed on to the shift of 3, shift of 3 means like from A, there is a shift of 3. So A is replaced by 1, 2, 3 by F. So this is the simplest symmetric algorithm. You just have a key which is pre-shared between the sender and the receiver. And based on that key, the recipient knows what needs to be done to reverse and get the message. Okay. Now this is the simplest symmetric algorithm. Now let's look at a traditionally used AES, right? AES has so many rounds. So it was just one step symmetric algorithm. Whereas in AES, you can see so many steps are there, right? So add round key, substitute byte, shift rows, mix columns, add round key. So this same steps have repeated 10 times. So there are around 10 rounds. So here the difficulty in breaking this algorithm. Think about difficulty in breaking the algorithm. So with Caesar cipher, the difficulty in breaking this algorithm is finding out what shift me and Barry has agreed. So if you try it 27 times, right? Maximum you have to try is 27 times, right? If you try that 27 times, somebody can break it. But when it comes to AES, if somebody wants to break it, they'll have to reverse the entire process, or they will have to find the exact key that is being used. Same like Caesar cipher. But when it comes to AES, the key that we use is 128-bit. Minimum is 128-bit. So what is the key that we have to search? 2 raised to 128 possible keys are there. You will have to search among this huge possible set of keys, and then only you can break AES. Hope that part is clear. If you want, I can simply clarify it again. Are we good on that part? Just to
I'm
understand, like,
concerned.
sorry,
Yes.
we are good, right?
Yep. Yep. Yep.
Okay, cool.
I wanted to add a comment. I noticed you asked if people have doubts. This is this is kind of a thing from your culture where you say doubts, and what you mean is, do you have questions? Yes?
Yes, correct.
Because I've been in meetings where that phrase was used and people thought they were being called liars or something, but that's not what it means. That's not what it means at all. What you mean is, does the audience have questions?
Oh yeah, I get it. Yes.
Every time I hear it, it makes me chuckle. Thank you.
Okay, so I meant questions. We are very used to using the term doubts. I just thought about it. Yes, it can mean that. Yeah. So here from this diagram, you just by comparing the simplest and the most advanced symmetric algorithm, the standard we are using today, you can simply understand like why these algorithms are so secure, because their security depends on searching the all possible keys that are required. So if you are using 128-bit key, you have to find out which among those 2 raised to 128 possible keys have you selected for encryption. Only then you can decrypt. So that's what is symmetric algorithms. Now let's go to asymmetric algorithms. So I have just popped so many equations in front of you. I just want to convey that asymmetric schemes are based on mathematical principles, okay, mathematical problems. So here you can see, you don't see any much math. Definitely there is some hardness assumptions and things that is related to maths, that's all there. But you can see it's more of like a shifting, rotation, mixing, substitution that's happening. So here it's just substitution that is happening, right? You are substituting A with something else. Here, there are something like rotation, mixing, symbol XOR and all is there. Here, there is no dependence on a core mathematical problem for security or building the algorithm. Whereas in RSA, the fundamental or the security reliance is on some kind of mathematical problem. Now, the mathematical problem that RSA relies on is factorization problem, right? So what is factorization problem? So if I simply ask, what are the factors of 15? You can easily say it is 3 and 5, right? 3 and 5 makes 15. Now, if I ask 21, you can easily say it is 7 and 3. But when I keep increasing these numbers, like when you think of a very large n, which is actually a factor of very large prime numbers, it gets difficult to factorize it. So, and it's not because we don't know how to factorize, it's only because it is computationally infeasible that you can run the algorithm for so many years, and by the time you actually maybe find the factors, it will be trillions and billions of years later. Okay, so the concept is that we don't have or at least we have not found a classical algorithm yet which can break or factor a large number, at least till now, right? So since we don't have a very efficient classical algorithm, we can say that they are unbreakable, right? So it's depending on something called computational feasibility or computational hardness, right? So it's not because we don't know how to do it. Yes, there is an algorithm that exists, but it's not within the polynomial time. The algorithm is not a polynomial time algorithm. Polynomial time algorithm means, like in simple words, you can say it is not within a usable period of time. Like you can run it forever, and by the time you get an algorithm, result from it, it will be like even we will perish. Like that's the time it might require, right? So factorization problem is such a problem which do not have a polynomial time classical algorithm. So we were safe to use it in the classical era, right? We could build cryptographic algorithm based on it, and that's what is RSA is, right? Now there is other algorithm which is called ECC, elliptical cryptography based algorithms. That is also based on discrete logarithm problem, which is also not having a polynomial time classical algorithm. So because of that, they were very safe to be used in the classical era, right? We cannot find a algorithm that can break it. Okay. Now just look at this steps, just to look at here. So here we have something called the public key and the private key. So as I mentioned, like when it is symmetric, we have the same key, Barry and me has the same key. When it is asymmetric, Barry and me has our own pair of public and private key. And Barry sends his public key and I will also send my public key. Okay. So here is the combination that we have. So here you can see E and N is the public key and D and N is the private key. Now what is N? N is that very large number which is a product of two primes. Okay. So if you actually can find P and Q, looking at them, see N is public, right? N is public value. E is also public, right? So here the only secret that you have to find is D. Okay. Now looking at this N, if you can find out this P and Q, using this E, you can find D. It's hard because looking at this N, nobody can find this P and Q. Okay. So that's like simple assumption there. So it's very difficult to find the value of D provided the public values. Okay. So RSA is built on the assumption that even if you have the public information with you, until you find the factors of this N, you will not be able to find the private values. Okay. So you got the key, right? If you want to break RSA, you have to go ahead and factorize these numbers. So till the time nobody can factorize that number, we are good to go with RSA, right? So that's our current crypto systems. So here is an example of RSA. So this is our public value. So this is our message. I do 2 raised to 5 mod and I got 4. And the person who is having the private key. Okay, so let's say this is Barry's public key. Okay, 5 and 14. And my message, which represents hello, is 2. So what I'm doing is I take Barry's public key, which is 5, and I power it like 2 raised to 5 mod 14, and I got a value. Now this is what I will be sending over the channel. Now Barry, when he receives 4, right, he has the corresponding private key with him. Now what he will do is he will power it up with 11 and then do mod 14, and he gets back the 2 which represents hello, and we are able to communicate, right? So this is basically how RSA works. Now looking at this 4 and looking at this 5 and 14, if they want to find 2, they should know this value for 11, right? How will they get value 11? They'll have to factorize 14 and then find out what is the factors, right? So it's as simple as that. Like till the time this large N is not factorizable, or like it is difficult to find the factors of that N, RSA is safe enough. Okay. Now let's go to hash functions, right? Hash functions are basically a certain category of cryptographic functions which gives you a like map of that input that you have, right? They are basically used for integrity assurance. So if you take the hash of a certain message and you keep it, now it should be very difficult to reverse engineer from that message, of course. But every time you pass the same input to the same value, you should be able to get the same output. So let's say I want to send some message to Barry again, right? So here we are not worried about the secrecy. Here we are more worried about the message content being modified. Okay. So what I'll do is I'll take my message. So let's say my message is we will have a meeting at 9:30. Okay. So here our worry is more about somebody making this 9:30 to 10:30 or something else, right? So here we are more worried about the integrity of the message content. Okay. So what I'll do is, along with my message, I will pass the message through the hash value, and I will send the hash value along with my message to Barry. Okay. So this hash value can again be signed using or encrypted using Barry's public key and send it so that only Barry can see it. So that's additional things you can do. But assume that he has securely got the hash value of the message. Okay. Now let's say during the transit, somebody changed the 9:30 to 10:30. Okay. Now, Barry can easily identify it. How? What he will do is, he will take the message that he has received, pass it through the same hash function, and match it with the hash value he has received. If both the hash values are matching, it means that the value that I have sent and the value that he has received, both are same, right? The message that he has received and message I have sent is same. Whereas, if Barry is getting a different hash value compared to what he has received, then he can immediately understand somebody has modified the message. So hash functions are basically cryptographic tools which helps you in achieving integrity requirements, right? So these are the properties of hash functions which can be achieved, applied to any block. It should be of fixed length, and there should be one-way property, and there shouldn't be any collision, etc. Right? Now, if you want to break a hash function, how can you do? You can simply find two values or like two messages which can have the same output, right? So let's say if Barry, when Barry is cross-checking, let's say somebody else changed the message to let's meet at 10:30 in France or something like that. So if somebody is able to find a message that has the same hash value as what the original message had, then there is no way to confirm that message has been modified, right? If somebody is able to find a collision, okay? So the original message is there and there is a fake message. If both these messages have the same hash value, then there is no way in achieving integrity. So in order to break hash functions, you can simply find collisions, okay? So what we were trying to discuss till now is the current cryptographic systems and how we can break them, like the cryptanalysis techniques that we have today, right? So to show you what hash functions are, like it is also something similar to symmetric schemes. You have some kind of shifting, then XORing, then some operations that you have, like then some map functions are there. So you kind of have certain operations that you do. So what I'm trying to convey is, again, the difficulty or the hardness is not based on some mathematical fundamental problem, the hard problem. Okay, it's also based on certain operations. Okay, so like you built in certain operations, you bring in non-linearity and all those stuffs into the functions, and like you try to map these functions into a the inputs into a output range, which is difficult to reverse. Okay, so that's it. Like, so that's basically hash function. So if you want to find a collision, what you can simply do is, simple thing that you can do is you generate all possible inputs and all possible outputs. Obviously, you are gonna get some collision because hash functions input map or the input domain is much higher than the output domain. So like, for example, like hash 256-bit. So your input is definitely higher than 256-bit. So the domain range, like the number of inputs and the number of possible outputs is much smaller, right? So if the input is, the possible number of inputs is higher, then there is always a chance that you can definitely find two values with the same thing. So there is some concept called pigeonhole principle. So let's say you have 10 pigeons and you only have 9 holes, right? 9 homes for them. So there is like, if you want all the pigeons to be occupying some home, there is always a chance that two pigeons will be occupying one home, right? Since the number of holes is lesser than the total number of pigeons that is there. So if it is, if number of holes is lesser, then of course, some pigeons have to share the home. The same concept is there with hash functions also, but we are relying on computational complexity again. So what we are telling is that it is computationally infeasible to find such collision. So that's why over time we have to shift onto the hash function. Like earlier days, MD5 was fine. MD5 was an algorithm we used to use, but today MD5 is said to be vulnerable. With any normal computational power we have, we can easily find a collision for MD5. Okay. So to sum up, like the classical cryptographic main algorithms in use, I have just given you a map table. So in hash, you don't have any concept of keys. And here you have symmetric and asymmetric. And under hash, the NIST recommended range is 256 bits. And symmetric, it is minimum 128 bits. And asymmetric, it is 2048 bits. Okay, so the commonly used hash algorithm is SHA, symmetric is AES, asymmetric is RSA. And in key management issue, with hash, there is no key management requirement. With symmetric, as mentioned, it is very critical that the key is secretly transmitted, right? In asymmetric, you don't have that overhead of key management. Now, effect of key compromise. If somebody's key is compromised, like not somebody's, if the key is compromised in symmetric, both sender and receiver has to redo the entire thing. But if in asymmetric, if Barry's private key is gone, it doesn't mean that my private key is also gone. Barry has to create a new pair, right? So only laws for the owner of the specific key. Okay. And speed is hash is fast, symmetric is fast. Whereas asymmetric, because of the mathematical complexity involved, it is high and it also requires high resources. Okay. So in practical world, we basically use symmetric algorithms for encryption and asymmetric algorithms for distribution of keys. Okay. So to distribute the keys, we basically make use of asymmetric schemes. So this overhead of key management, that is taken care by asymmetric schemes. Okay. So what we do is we have both the algorithms in place. Me and Barry exchange the key using asymmetric scheme. Now using that key, I will use symmetric algorithm to send the message. Okay. Let me just put my laptop on charging, please. I think it might.
We don't want your battery to run out during the presentation.
Yeah. Yeah. So next, what we are trying to understand is what is quantum computing. So quantum computing is basically computing utilizing quantum phenomena, right? So we calculate based on qubits, which can support computational, which can utilize quantum phenomena for computation, which certainly improves the solution capability or finding the solution capability of certain kind of problems. So we have to understand that quantum computing is not a computing setup that is like, it can be generalized as faster than classical computing. No, quantum computing solves certain kinds of problems. Now, what are the certain kinds of problems? That's what like these researchers analyze. So what we try to do is we try to map the problems into the quantum methodologies, right? So we break down the problem into representation of any kind of quantum related phenomenons theory. So we map into that phenomenon, and utilizing that methodology of mapping those into these phenomenons, we make use of these quantum principles to solve them, and then we finally arrive at a better solution. Like simple example can be searching problem, right? If you have to search over a large number set. So let's say there are 10 buckets, okay? Now you want to see if number 5 is in which bucket. You don't know any information about the bucket. You just know that there are numbers that's there in this 10 buckets. That's the only information you have. Now, if you want to know in which bucket the number 5 is sitting, right? You will have to go to one bucket one by one and then open the bucket and see in which bucket these like number 5 is there, and you will have to figure it out. Whereas when you make use of quantum phenomenons, you map it into a different kind of problem, right? You are not looking at, you are not actually figuring out the location of the number 5 in which bucket by like looking at each bucket one by one. So in classical phenomenon, if you had to look into the bucket one by one, so the worst case scenario that you will have to do is all buckets, right? So minimum 9 or 10 minus 1, 9 buckets you will have to open to confirm that at least if it is in the last bucket, right? Whereas with quantum phenomenons, what you do is you convert this problem into something called as amplitude amplification problem, right? So what you can achieve is you just look at the states of these buckets, right? So you just like uniformly consider all the buckets in the same state. Now what you do is you look into the internal setup of those buckets, and you actually flip the face of the bucket which has just 5, and then what you do is using certain quantum phenomenon operations, you amplify the amplitude of the location or the bucket in which you just have this particular value 5 that you're looking at, and by the end when you do the measurement you will get the bucket in which the number 5 was there. Okay, so or you will get to know the value 5's existence. If bucket 5 was not there, you will not get an output there. You will be getting like some error prone. You will not be getting a proper outcome. You will be getting some random values output, which you can using which you can confirm that value did not exist, right? So what we are trying to do is we are basically mapping our problems into some kind of quantum methodologies in quantum computing, and then we are trying to find the problem solution. So summary is quantum computing doesn't provide solution to doesn't provide better solution to all the problems in classical computing that we have. It only provides solution to certain set of problems. There are problems which is difficult to quantum computers even now, right? Quantum computing is not a computing technology which has the problem for all the problems that is there. It's not the case. It provides better solution for certain set of problems that was difficult to classical computing. And of course, it has its own impact, like it has positive impact as well as negative impact. Okay. Now, what is quantum cryptanalysis? Quantum cryptanalysis, as we discussed, cryptanalysis is basically trying to find the solution or the code that is in like securely transmitted or whatever. Like if we want to break the encryption, we have to find the secret key. If we have to break symmetric encryption, we had to factorize the numbers, right? If we had to like break hash algorithms, we had to find collisions, right? So basically, cryptanalysis is done using finding the like using brute force techniques, or by factorizing the number, or by like searching over a large range, etc. So quantum cryptanalysis, again, the same concept. What we use is we use quantum algorithms to attack these cryptographic systems, right? So the basic goal is again the same: break encryption, forge signatures, and speed of brute force, right? Now, when you try to map classical threats to quantum versions, so in classical version, brute force can be mapped using Grover's algorithm. Why? Brute force is basically searching, as I described, searching 10 buckets. That was basically brute force, right? If you had 10 possible keys, you will have to look at all possible buckets, all possible keys, which is there in all these buckets, to understand which was the actual key. So if you had 128-bit keys, sorry, if the size of the key is 128-bit, then you had 2 raised to 128 possible keys. So brute force was basically trying all possible keys, right? Now you can use Grover's search, right, to reduce the number of algorithms that you need. So the comparison, direct comparison is, if you had to try n steps in normal search, if you had to look at all the buckets, now with quantum algorithms, you just have to do the operation of root 10 times. It's not very different when the numbers are very small. So because if it is number is 4, n is 4, 4 becomes 2. It doesn't look like a huge difference. But if the n is very huge, it does have a quadratic reduction, right? So brute force in classical world can be mapped to Grover's algorithm. You can use Grover's algorithm to perform brute force in a much more efficient way. So if the earlier security level was 2 raised to 128, now in quantum world, the security level gets reduced to 2 raised to 128 by 2, which is 2 raised to 64. So if an algorithm, if a hash algorithm or like an AES had 128-bit security in classical world, with quantum algorithms in place, its security is reduced to 2 raised to n by 2. So if it had 2 raised to 128-bit security, now it is getting reduced to 2 raised to 128 by 2, which is 2 raised to 64 bits. Okay, security. Now, factoring large integers was the classical problem also, but we never could find any polynomial algorithm for it. So, but Shor's algorithm came. So, Shor's algorithm was the biggest, I'll say, motivating algorithm, even for me, like Peter Shor. He demonstrated the possibility of how quantum algorithms or quantum phenomenons can be used to solve a problem which is otherwise very difficult for classical computers. Okay. So Peter Shor's algorithm, was the kind of the first algorithm. There are other quantum-based technologies which prove to be well advanced. I'm not talking about quantum technology area. I'm talking about quantum computing. Okay. So a breakthrough or like a real practical scenario, right? How quantum computing can be groundbreaking, right? So that was actually demonstrated by Peter Shor's algorithm. So Peter Shor's algorithm was able to solve a problem in polynomial time, which was otherwise exponential problem in classical computing. So to give you a mapping, if it used to take like trillions of years in classical era with classical computing, it just takes hours, right? It's like under hours when you use quantum computing. So that is the difference. Like if it was exponential time requirement in using classical techniques that we have, whereas with Shor's algorithm, the time required reduced exponentially. Okay. Now the other thing is collision finding. So quantum collision algorithms. That's also again same like searching. So if you are able to generate a big table of all possible inputs and outputs. Now, classical computer is very weak in searching also, right? As I mentioned, if you have a very large set, you will have to search in this entire set and find the actual one. But if you have quantum algorithm, which is Grover's search, you can reduce the searching time much more better. So collision finding is also can be utilized. Collision finding can also be done with quantum collision algorithms. Okay. So when you map the impact of quantum computers, Shor's algorithm will help us factorize integers and find discrete logarithms for in polynomial time, eventually breaking RSA and ECC. So breaking a 2048-bit RSA algorithm requires minimum of 4098 qubits and 5.2 trillion Toffoli gates. See, there are a lot of studies with different resource estimations. I'm just giving you like one of the map. Okay, you can find. I'm not referring to any specific resource estimations because like this area is crowded, right? So you see people declaring that they have milestone achievements, and then there is debates over it. They are mostly talking about special case scenarios and all those things and all. Now, breaking a curve with 256 modulus requires a minimum of 2,330 qubits and 126 billion Toffoli gates. And Grover's algorithm will reduce the searching time. So here I have simply mapped the stuffs. So quadratic speedup, Grover's search provides on searching problems. So n is reduced to n root 10 steps. Exponential speedup is given by Shor's factoring. So from exponential time, we have gone to polynomial time. Okay. Now there are other algorithms as well. Why we are focusing on Shor's algorithm and Grover's algorithm is because they are the most referred to algorithms. There are other algorithms also. So one is Simon's algorithm. There is an exponential versus polynomial time speedup. Then phase estimation is there. Then there is HHL algorithm for linear systems. Then there is quantum walk search, etc. So see, it's simple concept. Like what we try to do is we make use of quantum-based phenomenon mappings or quantum-based, like we convert the problem into some kind of quantum algorithm or quantum-based phenomenons. So we can map and find the solutions based on that. Okay. So again, quantum computing doesn't provide a solution to all possible problems that we have. That's not the case. There are certain set of problems which is solvable for quantum computers. Unfortunately, a factorization problem fell into that set, and that's why we are facing or we are going through the biggest security revolution in the recent times. Like if the quantum computers, as said, will be a reality, we will have to replace our entire digital infrastructure because the dependence on public key crypto system is like we cannot take any application and say that it doesn't depend on public key crypto system today. Every single application and the internet, it requires and needs public key crypto system. So obviously, it is going to be the biggest security revolution that we are going through. So the impact, so this is actually the impact map by NIST. So here you can see the entire public key crypto systems are broken, and the symmetric algorithms, they are still considered okay. Only thing is that if we were using 128-bit earlier, we will have to increase the key size, right? So as we talked about, it will just reduce from 2 raised to n to 2 raised to n by 2, right? So if we need more security, you just increase the size of n. For some time, that's okay. So in case of symmetric and hash algorithms, you are fine with increasing the size of it. Whereas with public key crypto system, you are gone. Like you cannot find replacements. You just have to replace. You cannot find workarounds, right? You can only find replacements. There is no workaround in this area. You completely have to replace them. Okay. Whereas with symmetric and hash algorithms, you have workarounds where you simply can increase the size of the bit size or the output size. So the key size, if you increase for symmetric algorithm, you are good. And for hash functions, if you increase the output size, then you are good. Like if we refer to pigeonhole principle, if you simply increase the count of the pigeonholes, we are good for some more time. And if we refer to like symmetric algorithms, if you actually increase the size of the keys that is being used, then you're good. But with public key crypto systems, there is no way, unfortunately, we'll have to replace them with better schemes. Now let's talk about the practicality. Okay, so when we talk about all of this, like we have to discuss about the practicality of these things that we are talking about, right? So let's discuss AES 256. So that's the kind of standard that we have. We would need quantum Grover search with 2 raised to 128 operations, which is still very much infeasible today. Okay. So I have put some of the reasons below because in order to achieve this, we need so many qubits being able to communicate with each other without any error, which looks completely infeasible today. So AES 256, like there are a lot of studies which says that there is no Grover advantage on breaking AES schemes also. But we have to be optimistic and we have to see in security, if somebody says there is a possible viable threat, right? Then we cannot trust those schemes anymore. When we have not even identified threat, we cannot trust them, right? Now we have a critical threat that we have identified. Now we cannot keep trusting those schemes anymore, right? So obviously we'll have to go around with workarounds as mentioned. AES 256, if we increase the size of it, size of the key, then it's fine to be used for some more time. Okay. Then RSA 2048 and 4096, that's the practically used algorithms in today. There are a lot of studies. As mentioned, we will need a minimum of 2048 bits and all. We are kind of, there are a lot of people who claim that we have reached around 1000 qubit range and all. But no, they are not practical enough to solve a RSA problem. RSA problem, I mean the practical RSA in use today, which is 4096. Now, when we talk about hash algorithms, they are still relatively secure. As mentioned, they need Grover's quadratic speedup to be broken to find the collision. As mentioned, like it's very much infeasible today also. So what are these challenges? We have very few physical qubits, right? And even if we have like increase the size of these physical qubits, they are highly error prone, like error rates are very high, and they have very short coherence time as of now. Qubits lose their quantum state within microseconds or milliseconds. So these cryptanalysis algorithm requires circuits that is very deep in the sense like the length of the circuit is very huge, right? There are so many operations which you have to do. So the like if you depth means like on the same qubit, you will have to do operation 1 set of operation, then 2, 3, 4 like that. So if you look at the depth of these circuits, it's very huge. But by the time you reach a certain set of operation, they would have like fallen out of state. So again, you will not be able to perform those operations, right? So then connectivity issues in the sense like if you have certain qubit system that needs to be breaking this algorithm, you want all of these qubits to communicate with each other to achieve that quantum advantage, which is again practically infeasible when you talk about this higher size of qubits. Okay. So like summing up, I have just put down, like, with respect to hardware, we don't have enough qubits. Coherence time is too short and too much noise. Now with error correction, you know the concept of physical qubits, logical qubits mapping, right? So to build a very stable logical qubit, the number of physical qubits that is required is like huge. So to build a logical qubit system of certain logical qubit size, the physical qubits you need is very huge, which again seems practically infeasible as of today. Now, algorithm execution circuits are too deep, unstable to run end to end. So we'll need a lot of researchers are working on reducing the depth size of these algorithms as well. Now, scaling systems, control of millions of qubits is impossible as of today. And the theoretical understanding that we have, like most of the things that we do with are mostly theoretical understanding because we have not practically realized. So the expected quantum behavior of these systems at a scale is still unknown because we have not built it yet. So we are predicting these studies or results based on the things we have seen at the low scale, right? So when they are scaled up, what could be their behavior? It's practically unknown. So we have challenges in that angle as well, right? So now I'm talking about a lot of problems. Now, like I'm telling that it's infeasible, it's practically not feasible, etc., etc. So in that angle, if we think, we will feel like quantum cryptanalysis like an imaginary theory, but that's not the case. There is a theorem called Moscas theorem. Okay, so it's very, very critical. So currently, the estimated time for cryptographically relevant quantum computers. So cryptographically relevant means a quantum computer that can have an impact on classical crypto systems. The estimated time for them coming into existence is like there are a lot of debates on this. But what I have seen is personally like 10 to 20 years is the estimate that we have today. Okay. So what Moscas theorem states is that if the lifetime of your data, right? If the lifetime of your data is more than this period, okay? So let's think of the worst case scenario. Let's say quantum computers that can break RSA is going to come after 20 years, okay? Let it be after 20 years. It's not going to happen very recently. But if our data is relevant even at that time, so it could be high security related information, even our health records, or any defense related information, any critical information that has a lifetime of about 20 years, right? If we are using classical crypto systems to secure them today, we have a problem, right? What these attackers can do is they can save these critical information with them today with all the public key related information. They'll keep everything recorded. And by the time, like after 20 years, when these quantum computers are available, they'll break it, right? So what Moscas theorem states is that if your lifetime is higher, in simple words, if it is higher than that is, if x plus y greater than z, then we have a problem. What is x and y? How long do you need the encryption to be secure, which is actually related to the lifetime of the data. Okay. How much time will it take to retool the existing infrastructure with this large scale to build a quantum safe solution? He is also considering the time you will require to build a quantum safe solution. So here he is stressing onto that fact also. So let's say you have a very critical infrastructure that is dealing with information that is that is very sensitive, and the lifetime is very huge. Let's say 25 years. Now, if if the quantum computers can come in within that period, and if the sum of the time that you require for building a quantum resistant solution, if the sum of that is falling or greater than the time when a cryptographic relevant computer can come into existence is there, then you have a problem and you have to plan migration immediately. So that's what this Mosca's theorem talking about. And NIST has already suggested that by 2030, that is in 5 years, we should have migrated all of the critical infrastructure at least to quantum resistant solutions. So let's look a little bit into security in quantum era. So we can have quantum phenomenon-based solutions, which is actually encrypting and decrypting the keys that are derived from quantum principles, which includes the category called QKD, which is very famous, quantum key distribution. So what we do is basically, like as mentioned, in classical world, we used to use public key crypto systems to distribute the key, right? And we used symmetric algorithms to encrypt the message. So what we can still do is, since symmetric keys are kind of okay, we can continue to use symmetric algorithms for encryption, and for exchanging the keys, we can use QKD, quantum key distribution. But again, the challenges of quantum cryptography itself is a huge area. You would have learned about it, like there is hardware dependence issues, there is quantum channel related issues, so many things are there. So quantum phenomenon based cryptographic system basically deals with cryptographic systems that use quantum phenomena directly to build a cryptographic systems. Okay, so they are not relying on anything classical or anything mathematical. They're completely relying on quantum physics for building the crypto systems. Okay, so that is QKD, QSS, QSDC. QSS is quantum secret sharing. QSDC is quantum secret direct communication. Then we have QRNG, where we make use of quantum phenomena to generate random numbers, etc. Then we have other areas like this is very rarely discussed as a quantum resistant solution, but we do have the possibility of including physical unclonable functions. In my thesis also, I have made use of physical unclonable functions. They solely like current existing implementations could be vulnerable, but they complement other schemes very well in achieving quantum resistance. Okay, so physical unclonable functions can be used, or even physical or phenomenon based true random number generators, which can be converted into cryptographically secure random numbers can be generated from that. Then we have the major class that is like in high discussion today, like which is called post-quantum cryptography. So post-quantum cryptography, I'll call it as a advanced or like a next level of classical cryptography. So as mentioned, quantum cryptography, I'll not call it as a next level of classical cryptography because it's completely based on quantum phenomena. Whereas post-quantum cryptography is a class of cryptographic solutions which is dependent on mathematical problems which is resistant to quantum attacks. Okay, so why did we pick factorization problem? Factorization problem was picked in classical era because it was very difficult for classical computers. Now we will pick other problems which is very difficult for quantum computers and build crypto system. So the examples are lattice problems, multivariate problems, hash functions itself. So these kind of problems, which is very difficult for quantum computers, we pick them and build crypto systems. That is what is post-quantum cryptography. So NIST has already released the standards in this genre. Like they have suggested KEM schemes and PK signature schemes. That is key encapsulation methods and signature schemes. That itself is a whole together different session, which we can even, if you want, we can discuss. And then we can also be using combined architecture. As I mentioned, we can use QKD for key exchange and encryption schemes for like traditional symmetric encryption schemes for encrypting the message. Or even we can use PQC algorithms, that is post-quantum algorithms for key exchange. And then we will use classical symmetric algorithms for encryption. So that is the combined architecture methodology. So yeah, that comes to the end of the session. So like just as a summary, what I would like to convey is there is a lot of debates on if quantum cryptanalysis is going to be practically relevant, right? Theoretically, yes, it is very much relevant. But when it comes to practical feasibilities, there are a lot of challenges that quantum computing has to overcome to enable quantum cryptanalysis. Okay. So there are specific studies that people do today to enable quantum cryptanalysis. There are a lot of studies. But again, as of today, they are like from the studies that I've seen, they are predicted within the range of 10 to 20 years. These cryptographically relevant quantum computers are predicted within 10 to 20 years. So I will come back to Mosca's rule. So if our data is having a lifetime, it is critical for a long period of time. It is within that range that Mosca suggests. Then we have a problem. We should plan the migration immediately and go ahead with the quantum resistant solutions. Yes.
Very good. Thank you. Thank you. Thank you. This is an excellent talk. In fact, Mahima, I am jealous. I try to explain these concepts and I don't do nearly as good a job as you do. So thank you very much. I have some questions, but instead of hogging the scene and asking my questions first, I want to find out what questions other attendees have. So go to it. Unmute yourself. I can read questions from the chat, but I'd rather have people just unmute themselves and chime in.
Yes.
And if questions start bubbling up right away, then I'll ask mine. Go ahead.
I don't see so many questions here. So I see from William here, cryptographic capabilities.
Well, my usual process is to wait for usually what happens is when I say it's time for people to chime in, if you wait 20 seconds, someone will be brave enough to do it. So let's do that. Somebody
Sure.
ask a question. We'll be quiet
Yes.
here while we stare at the screen. Come on, somebody.
So I'll ask a question. I'll hog. I'm okay with that. You mentioned an algorithm, a quantum collision algorithm. I've never heard of that one. Is that based on one of the other classical gate-based quantum algorithms, or is it?
No, it's it's same like traditional quantum algorithms. Like you can create a combination of Grover with classical approaches, and you can build a collision detection algorithm out of it.
Okay, so it would be a collection or similar to Grover's or Simon's?
Yes, sir.
Okay. All right, thanks.
I have a question. You had said that actual quantum methods would use a purely physical process, not a mathematical one. But as a mathematician, I think that to the extent that we can understand it beyond phenomenology, all physics can be modeled with some mathematical model. even if we don't have it yet. So in that sense, a potential quantum physical scheme is only unknown in the same sense that no known polynomial algorithm is known for integer factorization. I'm not sure.
I somehow did not exactly understand the question.
Okay, I might not have quite understood what you were saying, but it sounded like it was that if you could have a quantum machine, say, not necessarily what we now consider like a quantum gate-based computer, but some quantum phenomenon that
Okay.
that would do the encoding, and you said this wasn't mathematical. My clarification would be, isn't this just mathematics that we might not know yet, in the same sense that we don't know a classical polynomial time factorization algorithm? That it doesn't mean that that doesn't exist, just that we don't know it yet.
Yes, agree. Yes.
Okay. Thank you.
My
I
interpretation,
totally agree. Yes.
my interpretation of what Mahima said is that with a quantum algorithm that doesn't rely quote unquote on mathematics, that means all the mathematics is buried inside the quantum phenomena, rather than when you do prime factorization, where the prime factorization itself is a phenomenon that doesn't have to do with quantum. So I think what you were saying there wasn't a rigorous elimination of mathematics. It was just a sort of, where does the mathematics belong in the solution of the problem?
Thank you, Barry. Yeah, that expresses it better than I did.
Thank you. Other questions,
you.
other issues? Well, I'm going to jump in with one. Where does P equals NP fit into all this? I've heard that quantum doesn't give us any clues about that, but then you mentioned that Shor's algorithm solves an exponential problem in polynomial time. How do we gel those two ideas?
So the classical NP and N set of problems, all P and NP all set is there. We have a different set called bounded quantum polynomial time, BQP range. So there are algorithms that fit into that range. So Shor's algorithm is fitting into that range. So it could be an intersection of NP or P algorithms, like it could be intersection of that. So what we have is BQP range.
Okay, but my
So
understanding.
what I want to say is that quantum, like not all NP algorithms can fall into BQP range. Some of the NP algorithms fell into BQP range, that because we have realized a quantum solution for that.
Okay. So the fact that you're calling prime factorization exponential does not drag NP problems down to polynomial time solution with quantum machines. Is that correct?
No.
Okay.
Not all of it, yes.
Prime factorization is verifiable in polynomial time. That's the P part of NP.
That's the N part of NP.
I N part, got that backwards. But yeah, the verification is polynomial.
Right.
There are conceivably, that's the question, problems which would take as long to verify the solution as to solve. That is not known.
Okay. All right. Other questions? Well, I'll go ahead and ask mine again. Right. What's wrong with AES? The only thing that I saw you throw at it is Grover's algorithm, and that doesn't make an intractable problem tractable. It just does square root speed up. Why
Yes.
can't we call say AES is good enough and live with it? Why do we need more fancy post-quantum cryptography?
Oh, yeah. Sir, with symmetric schemes, currently we are not planning to replace them. We are good with AES itself. What we are trying to replace is asymmetric scheme genre of algorithms.
Okay.
So if you remember this slide, see, here is where we have identified the problems, no? So this is kind of like good enough to be like we can increase the size and we are good enough, as you were thinking exactly. But they are not called post-quantum algorithms because post-quantum algorithms is a family of algorithms which is built like based on mathematical problems that is resistant to quantum attacks. So under that, these symmetric algorithm doesn't fall, right? As I mentioned, like lattices, multivariate, all those kind of problems we have picked them up and we are building crypto systems out of it. That is what is post-quantum cryptography.
So let me summarize what I think you said, and you tell me if I'm correct. Um,
Yes.
Symmetric algorithms are considered to be safe right now and will be safe once we get Grover's algorithm working and other things. But asymmetric cryptography will not be safe, and we need asymmetric cryptography in order to exchange keys.
Yes.
Got
Yes.
it.
Yes.
Okay. Other thoughts or questions?
If I could chime in on that, in practice, there are two different use cases. I think this was explained in the talk, but there are two different use cases, what we call data in motion and data at rest. So for data in motion, which is just transmitting over a channel, the keys are typically only short-lived. So even if you have the best algorithm in the world, you might not be able to decode that in time before the next chunk is encrypted with a different key. It's data at rest that is the problem, where you've got all the time in the world to attack it.
Yes,
Okay.
I agree with that. And even the data in motion, these attackers can keep hold of them, save it for later purposes also. So that's what Mosca is also trying to address.
Yeah,
Yeah, but
thank you. But
there's a lot of use cases where people have stored private keys that they use for long periods of time. So those are subject to quantum cracking in the future.
Yes.
I hear that people are storing up information now that's being passed among us in order to eventually attack it with quantum.
Cache now, decrypt later.
Yeah.
That's definitely going to be a problem.
yeah, I think it's safe to say that if you've transmitted it over a public channel, it is potentially stored somewhere.
Yes, sir. Yeah, yeah.
More questions, comments, reactions, responses.
Well, just to comment, I really enjoyed this presentation. I like the fact that she provided a little bit of history or a little bit of mechanism on how the encryption works. A lot of these talks I've seen, they just gloss over that, just assume everybody knows that's two-part keys and the whole internet runs on it. Don't worry about how it works. But this is really nice. Thanks.
I second that. I very much enjoyed your elegant and clear explanations together with your slides. Really top notch.
Thank you.
Mahima, thank you so much.
Yeah, thank you, sir.
And thank you for everybody attending. And we'll be posting soon more Chicago quantum meetup events. Please stay tuned on our meetup channel.